Thank you for joining us today. I hope you had good lunch. So let me get started by introducing myself. My name is Snehal Nagmote. I work for e-commerce search team at WalmartLabs. Before joining WalmartLabs, I have worked at building distributed and systems data pipeline at Goldman Sachs, JP Morgan Chase, and Intuit. So today's agenda for presentation is, I'll talk about WalmartLabs problem domain and use case, and why we use Lambda processing. Then I'll walk you over our near real-time architecture implementation and some of the application tuning and lessons learned while productionizing this pipeline. So at Walmart.com, our goal is to provide our customers seamless shopping experience. The products which are sold on Walmart.com are by suppliers and merchants for .com and stores. So once seller comes in and he enters the product through catalog, the product has to go through item setup process. In item setup process, we categorize and normalize the product. Then for the same product, there can be multiple offers which can come in from different suppliers. So for instance, if I have to, or Walmart has to sell banana, that banana can come from a supplier from New Jersey or California. But whoever has the lowest price, that becomes as the primary offer. Also, shipping logistic and price adjustment information would be fed into the system. So shipping logistic help us to determine how fast we can deliver that product to our customers. So once item has set up, it can also go through changes throughout the life cycle of the product. But next goal for us is to index that product and make that product searchable on .com. So to do that, before near real-time indexing, we used to run a batch process. And that batch process used to run once a day. So there was a 24 hours latency from item setup process to our e-commerce search pipeline. So we wanted to improve that process and also improve our customer experience. So we built our near real-time indexing using Spark streaming. With the help of near real-time indexing, we can update new product information. Also, if there are changes to existing products, so if offer information changes, or online availability information changes, we can actually update our system. So with near real-time indexing, we can update this information almost every hour. Scale-wise, currently we are processing 2,500 to 3,000 events per second for an RT indexing pipeline. Also, Walmart.com has wide presence in stores. So one product can be present in almost 5,000 stores. So we get a lot of store availability events. We get almost 20,000 events per second for our store availability pipeline. Store availability pipeline is very important for us because it empowers the features on .com like Pick Up Today. Pick Up Today feature allows customers to buy item online, but they can pick it up from stores. So that means with this pipeline, we can actually update our store availability information almost real time. So the latency for this pipeline is sub-seconds. All these pipelines were built using Spark streaming. So let's look at our motivation for Spark. We use Spark because our batch pipeline were already using Spark. So we wanted to maintain the same code base and also to ease debugging, also faster production development. Also at that time, in our team, we were actually leveraging Spark for different data science projects. So we wanted to be on the same technology stack. So let's look at some of the challenges which we face while moving away from batch system to real time. The first challenge was how do we merge the real time data with historical signals data which was updated by different pipeline at different frequency. Then keeping the value of a few attributes consistent which was getting updated by multiple pipeline update. Also in general, if you make the code changes or your configuration changes, it's difficult to maintain different versions of data in your real-time streaming pipeline. Another challenge was how do we automate the start and stop of our Spark streaming components. So let's quickly look at our data set. Our data set is actually structured product attributes. So let's say if you go to Walmart.com and search for television, and you build your own search system. So to show TV results in search, you need very basic attributes. You will need availability information, you will need pricing information, and title and description. So we get all these attributes from our real-time pipeline. But if you search for specific query like Samsung TV, that means now your search system needs to understand that Samsung inquiry is basically a brand. So often this information is calculated by machine learning pipelines. In our case, we have a lot of machine learning jobs which calculates this information and make our search system to do ranking so that it can actually show relevant search results. So we calculate this batch computed attributes once a day, and for indexing products, we also need to store this information with our real-time pipeline data. That means we need to merge the real-time streaming attributes and batch computed attributes while indexing. To do that, we use Lambda architecture. So let's look at or understand what Lambda architecture is. Very high level, Lambda architecture is actually a term coined by Nathan Mars to do distributed fault tolerant processing, which can take advantage of both real-time and batch pipeline. The way it works is your input data is fed into the system, both real-time and batch. Then you apply your business logic transformation twice, once in the real-time, once in batch, and then you stitch together the results computed by both the system to form the complete data set. Traditionally in Lambda architecture, your batch layer has all the data set. So it has a master data, so it has complete data set. While your real-time system actually compensates for the high latency throughput updates, and it always works on real-time data. So in our case, we use Lambda to do the merging of our streaming attributes and batch attributes. So we use Cassandra to merge streaming attributes and batch computed attributes. So in this diagram, S1 and S2 are the attributes which are coming from streaming pipeline. These attributes are getting updated every few seconds, while B1 and B2 are the attributes which are getting updated by relevance signal pipeline. So these attributes gets updated once a day. So in the back end, what happens is we have the signals data science pipeline, which runs once a day, and input to this pipeline is actually item attributes. This item attributes is calculated by our batch pipeline. So the item attribute information in the index data is same as our streaming attribute, but the only difference is this item attributes is a complete data set. So also another input to our signal pipeline is our customer data, which is a customer interaction data. What products customer is buying, which category path customer is browsing products to, so that we can actually improve categorization score. It looks at 90 days of our customer historical data. So once signal pipeline runs and it calculates few attributes, those attributes are updated into Cassandra from HDFS to Cassandra. So we have a bulk uploader job which moves data from HDFS to Cassandra. Then SP1 to SP22 are the attributes which can get updated by both the pipelines. So it can get updated by streaming and batch as well. So to make sure the value of that attribute is consistent, we actually, so each client which is updating Cassandra uses timestamp feature so that Cassandra takes care of the updating latest value. So once data is merged in Cassandra, we further use it for XML processing. So that's how we use this data using Lambda architecture. Now let's look at our end-to-end indexing data pipeline architecture. The components which are below dotted line represents our batch data pipeline, while the components above is represents our near real-time indexing pipeline architecture. So the first component in this diagram is Spark streaming component. We call it UIS reader. The input to this component is two Kafka queues, product updates and offer updates. So if there is change to any product title or description, all those change events goes to product updates, while offer updates contains the change events related to pricing or online availability information. So this Spark streaming component reads from two Kafka queues. It applies the join on two D streams. It deduces the product ID, and based on product ID, then it queries the external Cassandra. So this is the external Cassandra which has all the up-to-date information, and it's maintained by different team. So once, depending on the set of product IDs, it gets the raw product data. So this raw product data is actually fed into UIS reader. And once US reader gets this raw product data, it applies the transformation and business logic on top of it. It converts that raw product into search product attributes. So those search product attributes are further returned to our search Cassandra cluster, where the Lambda merge happens. So it already has those patch computed attributes which are updated by product ID. So the merge happens between streaming and patch. Further, it also writes the change product IDs, the product IDs which were updated in search Cassandra cluster to different Kafka queue. Then we have a second component which we call as XML generator. This is also a Spark streaming component. It reads these product IDs, gets all the data required for generating XMLs, generates these XMLs, and then further it push it to Solr Kafka queues. And each Kafka queue here represents one shard in Solr. So once XMLs are in Kafka queues, then we have a Java consumer which consumes from this Kafka queue and creates the incremental index snapshot. These incremental index snapshots are further deployed onto search production Cassandra cluster. So the latency from US reader to creating index snapshot is just a few minutes, but then we are little conservative about deploying our index to search production Cassandra cluster, so we run series of regression tests, and that takes time. So while implementing this pipeline, there were few implementation considerations which we needed to make. How do we do the reprocessing of data if one of the Spark streaming component fails, or if we stop streaming component, or even if the code has changed? Then event ordering was very critical to our system because we wanted to process the item updates in order. Another criteria was synchronization of configuration update. So the component which was generating XML, that configuration and Solr configuration has to be deployed in sync. Then automating of start and stop of streaming component. So we still do our offline indexing which runs once a day, but when offline indexing is in progress, we stop our streaming component to make sure the index update doesn't go in inconsistent state. So let's look at how we solve all those implementation considerations. So our streaming component is actually using Spark streaming receiver approach. So to read data from Kafka, multiple Kafka queues, we dedicate to certain receivers, so certain cores, just to listen data from Kafka. And once those cores brings in data, we call it receivers. It actually push data into Spark memory. Then we have dedicated cores to process that data. So for solving reprocessing problem, we store our offsets into Zookeeper. So as soon as streaming component reads data from Kafka, it writes back that okay, this is the offset I have seen to Zookeeper, so that so if you stop your streaming component and restart it, it will start processing from where it left off. Then our Kafka queues are partitioned by item ID. That takes care of that all the updates to the same item are actually going to the same Kafka queue. And the end Kafka queues, which are actually input to Solr, so these Kafka queues are, it just have one partition. So it makes sure the item IDs which were belonging to the same shard, the updates also goes to the same shard. Then each of our streaming component is deployed using custom Ansible scripts. So what it does is, as soon as Ansible script starts our streaming component, it captures the job ID which was submitted to Spark master, and then it writes back that job ID to our MySQL database. And then when we want to stop our streaming component, it calls the Cronus API. So Cronus API is just a HTTP REST API. It's an internal name for the REST API, and that API gets the job ID for corresponding job from MySQL database, and then fires the Spark submit kill command to stop the Spark streaming component. Then in case of, so we process data in Avro, that helps us in taking care of different data versions. Spark streaming component, each of the streaming component writes logs on the Spark local. So we have application logs and Spark logs separate, and these application logs are further processed via Elasticsearch, Logstash and Kibana for further debugging if there are any issues in the application. So we can always look at Kibana and figure out what's going on. Also we have extended Spark metrics API for further monitoring. So we extend the source API and then we create our own custom accumulators and gauges. So for instance, if I want to figure out how many different type of business event I have seen, so I can actually create a custom accumulator for that, and then depending on my business logic, I can update the value of that accumulator. So when my application would be running, that accumulator value would be reflected on Spark REST UI, which has all other metrics displayed with the custom accumulators. And then we have custom monitoring agent, which actually pulls those metrics and then push that data to Graphite. So this monitoring agent continuously runs, and on top of Graphite, we have Grafana for visualization. So we just talked about monitoring. So we use custom accumulators and gauges for the key metrics. With addition to that, we also monitor scheduling delay and processing times for Spark streaming. And then we have different alerts set up on scheduling delay. Since we write our offsets in Zookeeper, we have some custom scripts which actually pull those offsets from Zookeeper in addition with the Kafka command. So we built this Kafka consumer lag, and then from Graphite, probably we'll move, we are planning to change this Kafka consumer lag with Burrow. So let's look at some of the application tuning which we did. The first thing you will require is to keep your Spark streaming application stable is your scheduling delay should be equivalent to 0. So even if it increases, then it should actually come down after a few batch processing. Scheduling delay depends on a lot of different factors. So it depends on your processing time and batch time. So your batch processing time should be less than or within your batch time. Then you should partition your RDDs effectively. So it should be in terms of multiple of Spark workers, because that's the maximum degree of parallelism you can achieve. Also, while reducing, if you want to reduce the number of partition in your RDD, you should actually use the coalesce over repartitioning. But if you want to increase the number of partitions, then you can pay the cost of shuffle, because repartitioning causes the shuffle. Another very important parameter is streaming back pressure enabled. So before Spark 1.5, this parameter was not there, and Spark doesn't do well if you have lot of batches queued up in processing. So we have seen Spark application going down really once in a while when this parameter was not there. So with this parameter, you also have to tweak your receiver max rate. So this parameter helps you to not, so Spark doesn't, if you set it to true, then Spark actually doesn't push lot of blocks or data into Spark's block generator. Then another parameter is you should use shuffle consolidated files equal to true. It improves the performance of shuffle by reducing the intermediate files. So let's look at some of the lessons learned. So we use Spark Cassandra connector while querying Cassandra. And we had a use case where we wanted to query Cassandra for a few keys, and our key size was almost 2000 to 3000. So what first option does is it will pull all the Cassandra table, and then it will apply the filter on Spark side, and the performance is really bad. Another option is you can use the where clause on Cassandra table, but internally what it does is it actually executes the inquiry clause, and inquiry clause is very inefficient. So little more about in clause. Let's say you have Cassandra cluster of 9 nodes with replication factor 3. What happens is, and you want to query for A, B, C as 3 queries. Your client will actually schedule those requests, but those requests will go through the single coordinator node. So, and your coordinator will keep both the request and response in the heap. So it puts a lot of pressure on your coordinator node. And in case of failure, if one of the query fails, if querying to A fails, then coordinator node will retry all the queries. So the performance of in clause is very bad, especially if you are using 2000 to 3000 keys in clause. So Cassandra connector already has the best option. You can do the join with Cassandra table. So Kafka RDD here is basically your list of keys, and from list of keys you can create a Spark RDD, and on Spark RDD you can create the join with Cassandra table. So internally it performs the internal inner join, and your queries execute asynchronously. So another important parameter is Spark locality weight. This parameter actually tells you the performance of shuffle over the parallelism. By default, the value of this parameter is 3 seconds. So there are two scenarios when you want to modify this value. First, if you have batch and you have lot of data, and your batch is taking longer time than your expected batch processing time, and after debugging you realize that only 1 or 2 tasks are getting executed as local. That means other tasks are still waiting, and then probably shuffle is in progress. So since you have lot of data, you are paying the cost of shuffle. So in that scenario you may want to increase the value. And second scenario is basically if you have a batch and you have a really smaller data set to process. So and still the batch processing time is lot higher. In this case you can actually pay the cost of shuffle and use your Spark cluster. Then Spark Cassandra connection keep alive is basically, since we connect to Cassandra, so by default the value of this parameter is 5 seconds. You should keep the value of this as multiple of your batch sizes. Then last but not least, cache RDDs whenever you can. It does not require any extra hard work, and if you are reusing your data, it just helps you to improve the performance. So that's all I had. Thank you. Any questions?
I have one question. So you mentioned that you store the offsets in Zookeeper from your Spark app. So I was wondering why you did that, because I know that Kafka used to store their offsets in Zookeeper, but then they moved away from that because the performance was really bad. Don't you have that same issue when you do it from your app?
So, so the question is, why do I store the offsets in Zookeeper? And Kafka was already doing that, and Kafka moved away from storing the offsets in Zookeeper. Yes, Kafka 0.9 actually moved away from storing offsets in Zookeeper, and they store offsets in Kafka topic itself now. But we started storing when we are using 0.8.2, and we haven't seen any performance issues as of now. But since our scale is still not in billions, but I think if we reach scale in billions, then we would be connecting and reconnecting to Zookeeper, and that's when the problem can start.
Okay, if there are no additional questions, thank you very much. The next talk will begin at 2:40.